Okay guys, before we crack on, before we move on to vectors and scales, I thought it might be worth just recapping some trigonometry with everyone. Now, two things. First off, this is about my sixth attempt to make this movie. I've gone off the scale here in terms of making silly mistakes or having to restart. So this time it's hell for leather, here we go. Now the other thing is, if you're studying trigonometry in maths at the moment, or if you've done it recently, what I'm going to go through now is going to be very patronising and silly. You'll have definitely gone through it in more detail and much more clearly with your maths teacher than I'm going to do it now. I'm just doing a very brief recap towards the physics side of things, okay? So I apologise if this is patronising. We've got to make sure everyone's on board before we crack on. So let's have a look. When we talk about trigonometry, what we're really talking about is the relationship between the sides of a right angled triangle. So I'll just draw an example of a right angled triangle. A right angled triangle is just any triangle that has a right angle in it. So you see there it's 90 degrees between these two sides. So any triangle that has a 90-degree angle in it. So that's a right angle triangle. Or let's try to do it over here. That's also a right angle triangle because it's got a right angle here. Doesn't matter too much about the other angles. There's always going to be a right angle in that triangle. Okay, so I'm actually going to start off with the hardest thing first. We're going to look at the trigonometry side and then look at Pythagoras' theorem, which is relatively handy in comparison. So first off, let's get some names on this fella. This is our right angle. We're always going to be interested in one angle here, one angle that we're trying to kind of find. And it's going to be this fella here, and I'm going to call it theta. Okay, so the names of the sides. There's always going to be directly opposite the 90-degree angle. It's going to be the longest side of the triangle. No matter how you draw it, the side across from the 90-degree angle is going to be the longest. And this gets its own special name. It's called the hypotenuse. The other two sides of the triangle are named depending on where they are in relation to this angle we're looking for, this theta. So the one that's beside it here, see the way this side is right beside theta? Another word for beside is adjacent. And we call this the adjacent side. And similarly, the side that's directly across from the theta, the thing we're looking for, is opposite it. So it's called the opposite side. So these are the three names we're going to be throwing around when we're talking about our trigonometric ratios in a moment. So the hypotenuse is the long part, adjacent is beside theta, the thing we're looking for, the angle we're messing around with, and opposite is across from theta. Okay, so the trigonometric ratios. First off, before we even talk about them, I want you to point out one thing. If I extend this triangle, let's say I keep the sides the same, sorry, the angle the same, right? Let's say I made it bigger. Let's say I just extended it a bit more in that direction. But I kept all the angles the same. So this is still going to be a right angle. This is still going to be the same angle. They're similar triangles. This angle is always going to be theta. This angle is always going to be 90 degrees. And whatever this was, just because I've extended it, it's the same angle. It doesn't matter. And I can go bigger, I can go smaller. It doesn't matter. What this is telling us is that the ratio of the sides will be the same. If I divide the hypotenuse by the adjacent here, it's going to be the same as if I divide this hypotenuse by this adjacent. That's really what the trigonometric ratios are useful for. So, what are the trigonometric ratios, I hear you ask? Okay, well, I've got a way of remembering it, mnemonic, that I was taught, which has worked for me. Now, if you're not into animal cruelty, you might need to think up your own. But the way I was taught it was silly old Harry chased a horse through our attic. Some people just remember it as Sakatoa. Sorry, it's a little bit off the screen. Let me pull this down a little bit. Some people remember it as Sakatoa, or come up with their own acronym. If you come up with one that's free of animal cruelty, that's probably the best, because horses don't belong in attics. Silly old Harry chased a horse through our attic, but that works for me. What that tells us is it's just a way of remembering which one's which. Now, you don't have to memorize this, but the more comfortable you are with them, the easier time you'll have it. So silly is for sine, old for opposite, H for hypotenuse, C for cosine. So here's what I prepared earlier. Sine is equal to opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Just move these over here for a second. And remember, we're talking about the relationship between the sides of a right angle triangle. So for this angle here, if I want to find the sine of this angle, I just divide this distance by this distance, opposite by hypotenuse. If I want to find the cosine, I can divide adjacent by the hypotenuse, and if I want to find the tan, I divide the opposite by the adjacent. So it's always using two sides to find this number. Now, Depending on the problem you're given, you might have to use one of these three. So if, for example, you know what the opposite is and you know what the hypotenuse is and you're trying to find out what this angle is, all you got to do is divide opposite by hypotenuse and you'll get the sine of that angle. And then it's just one step away from pressing inverse sine on your calculator, which we'll be talking about in our live lesson. In fact, let's do it now. Let's do one. Why not? Okay, so for example, I think that triangle, and this, by the way, is just an example. That's the crucial bit so far, is that those the formulae and these are the words that refer to it. But let's just test an example. I've just sketched this triangle roughly. Okay, it's not been very neat at all. But this side here is 10 centimeters in my case. My just random example here. And in fact, it looks like I've done a pretty decent. It looks like they're both 10 centimeters, but just by chance. In fact, some of you are already probably screaming at me what you think this will be. I've got about 14 centimeters here. Okay, so in terms of calculating, right? Let's see. First off, we're talking about theta here. Let's see if we can figure out what the angle is. I think that angle is about 45 degrees. All right, if this is 10 and this is 10, this should be about 45. Let's find out. In fact, it will be because of our measurement. But let's see how accurate my measurement is using hypotenuse. So I'm going to go with sine, okay? I'm going to find out what the sine of this angle here is. And the sine is opposite over hypotenuse. So 10 centimeters divided by 14. 10 divided by 14. We'll give a number, which is 5 over 7. Now, what that tells me is that the sine of this angle theta is equal to 5 over 7. Okay, so far so good. How is that useful? Well, it's useful because you can then figure out what sine is by using the inverse sine button on your calculator. So I'm going to press the second function, or shift, press the sine button, and it's a little sign with a -1. I don't know if you can see that. Ooh, the lamp is a bit too strong. So I press sine. Let me try that again, okay, just so it can be clear. So first I'm going to divide 10 by 14, so opposite by hypotenuse, which gave me this 5 over 7. Then I'm going to try and get the inverse sine. So I'm going to press shift and sine, and I'm going to see of the answer of 5 over 7. And this tells me that it's pretty close, 45.58. So that's telling me that this angle is about 45 degrees, which is what we expected. So the ratios work. Okay, we'll try a couple more of these a little bit later. But now I want to actually move on to something easier. Okay, so just before we finish with the trig ratios, depending on the sides you're given, you can use these to calculate the angle of theta. Or if you're given the angle of theta and you know one of these, you can use it to calculate the other. They are really, really useful, and we'll be looking at them in the context of some questions, which will help it make a lot more sense. But those are the basics. Okay, speaking of basics, we're going way back in time now to finish up. You'll be glad to know we're almost done. We're going to look at Pythagoras' theorem. Okay. So you were probably taught Pythagoras' theorem as a squared plus b squared is equal to c squared, or c squared is equal to a squared plus b squared, the other way around. It doesn't really matter. But again, it's talking about a right angle triangle. So I'm just going to sketch down. I'll try and accelerate through this because this is a lot easier than what we were talking about before. So there, I've just made a random right angle triangle. There's the 90 degrees part. There's that will be our theta if we're talking about trig, but we're not. Going to keep things much easier. Okay, so first thing I'm going to change here is instead of saying c, we've already learned that the long part of the triangle is called the hypotenuse. So I'm just going to say that a squared plus b squared is equal to hypotenuse squared. All right, it's not a trick or anything, it's just to make it a little bit more consistent with our earlier learning. Okay, now what this means is if I took the other, so that's h, and the other two sides of the triangle are a and b. It doesn't matter which is which, so say that's a, that's b. Okay, I could do it either way. What this is telling me is that if I took whatever distance a was, so like 8 centimeters, and squared it, added it to the square of b, I get the square of h. It's totally true, it always works, but a lot of people don't picture why it works. And the key to remembering is when we say the square of a, we are literally talking about the square of a. So what that means is, let's say I took a as the bottom bit, right? And I made a square out of the bottom part. So I made a square with the length, the sides of a. So if it's a across, I'm going to make it go an a down. So I said it's about 8 centimeters. Let's go down about 8, about there. So if I made a square out of the bottom of the triangle, it would have an area of a by a being a squared. That area there is a squared. Similarly, if I do the same over here, if I made a triangle out of b, I'm kind of running out of room on my whiteboard a little bit, but let's say that this is an area of the square b by b. If I took this area and added them together, they would equal the area I could make using a square of length h. That's what it literally means. That's what hypotenuse is talking about. Sorry, Pythagoras is talking about hypotenuse. So if I took the square of this side, it would be equal to the sum of these two fellas. A squared plus b squared is equal to c squared. Or in our case, we're going to use h squared. Right, I don't want to overload you. That's a lot of trig for 10-minute burst, or whatever this works out as being. Now, this will become a lot more clear when we're trying some problems on them, okay? And I'll be running through them with you. But that's just a brief recap before we move on. Okay, I'll talk to you soon.